It is my great pleasure to welcome Dr. Leilani Battle. Dr. Battle is an assistant professor at the University of Maryland in College Park, where she leads the Battle Data Lab. She holds a joint appointment at the University of Maryland Institute for Advanced Computer Studies and is an active member of Human-Computer Interaction Laboratory. She received a Bachelor of Science in Computer Engineering from the University of Washington, an MS and a PhD from MIT, where she was a member of the MIT database group. I invited Dr. Battle here today because her work is a fantastic example of integrating multiple disciplines. She uses HCI visualization to integrate data processing or databases with interactive interfaces. She is an absolute rising star in the field of information visualization, which is illustrated by her numerous awards, a few of which I'll mention here. Dr. Battle received an award for being 35 Innovators Under 35 by MIT Technology Review in 2020. She also received an Adobe Research Award, an NSF Graduate Research Fellowship, and an NSF Research Innovation Initiative. It is my great pleasure to welcome Dr. Leilani Battle.
So I'm pretty excited today to talk about kind of a larger arc that I've been working on in my research, which I've been calling for a long time behavior-driven optimizations for big data exploration. So the premise of my work is that whether you're in industry, government, etc., organizations all over the world are becoming more data-driven over time, but many of them are struggling to keep up with the massive amounts of data that are being collected from various instruments, devices, online services, and more. So with my research, I integrate methodology and techniques from data management, human-computer interaction, and visualization in an effort to help a wide range of people explore their data in intuitive but also interactive ways. And in particular, I'm interested in seeing how I can help people explore their data through visualizations. So intuitive images created of data, where people use visualizations to extract patterns, identify anomalies, and debug their analysis workflows. One thing I focus on in my work is seeing how researchers and developers can find new and innovative ways to integrate data processing systems with visualization systems, where data processing systems focus on applying complex computation efficiently to large data sets, and visualization systems focus on taking that computation, the results of it, and then representing it in intuitive ways to a wide range of people. So the key idea or the key problem behind my work is that we should be designing systems, not just to make the systems in themselves fast or sleek or whatever, but to help people achieve their goals in using those systems. So whether you're collecting data, whether you're trying to manage it efficiently, whether you're trying to render it and interact with it, all of these different kinds of systems are designed to help a person extract insight from their data. So if we want to build effective systems for data exploration, we have to consider not only the system performance, but also human performance considerations. So to address this goal, I organize my research along three major axes. I call them optimizing exploration, characterizing exploration, and benchmarking exploration. So in optimizing, the idea is to design these effective systems. But in order to do that, you have to characterize what it means to actually explore data in the first place. So what does it mean for a person to explore their data, and how does that exploration unfold? And what is the role of a system in that exploration process? And then finally, with benchmarking exploration, the idea is once you've designed these systems, you want systematic, repeatable, and transparent ways of evaluating and comparing them. And benchmarking can help us get that. So for sake of time, I won't go over all of my work along all three of these axes today. I'll be focusing primarily in optimizing and benchmarking exploration, so my work in those two axes. But some of my work in optimizing exploration does touch on the characterization aspect, and we'll see that later. So even though I'm focusing on just a few of the projects that I and my lab work on, I do want to highlight that I do other work in visualization databases as well. For example, enabling interactive debugging of database management systems, say debugging of database queries, SQL queries, for example, characterizing people's exploration behavior in different systems, such as Tableau, and then exploring and analyzing how people design visualizations on the web, such as using visualization languages like Deep3. So for the rest of this presentation, I'll talk about a particular exploration use case I studied in my thesis work. So exploring NASA MODIS satellite imagery. I'll talk about how I developed a system called Forecache to optimize exploration for that particular use case. And then I'll talk about how I've been broadening my research more recently to evaluate exploration systems in other contexts. And then I'll talk about some of my ongoing and future work. So let's talk about this use case. So in my thesis work, I studied how a range of scientists, primarily Earth scientists, explore NASA MODIS satellite imagery data, where MODIS stands for the Moderate Resolution Spectroradiometer. So MODIS was interesting from a database perspective, because I originally, as a grad student, was working with the database group at MIT. So MODIS was interesting from a database perspective because it's a huge amount of data that you could use to do a lot of different interesting computations. So for example, you could calculate vegetation density from NASA MODIS data, you could track hurricanes, you could track phytoplankton populations in the oceans, and you could also, in the use case that I studied in particular for my thesis, measure snowmelt or snow cover on different parts of the Earth remotely. And just to show you a little bit, a tiny piece of what NASA MODIS looks like. So you'll have the spatio-temporal attributes that people work with, latitude, longitude, and time. The MODIS is used to measure many different wavelengths of light, which are referred to as MODIS bands. For example, you see B4 and B6, those are bands B4 and B6. You see B1, those represent, like visible light bands or near infrared light bands. And you also see some metadata. For example, you'll see land, sea, mask. All that means is, oh, this particular part of the Earth that MODIS measured is a land portion or a ocean portion or something. And something I want to stress here is that just 2 weeks of NASA MODIS data was 10 terabytes uncompressed. So if you can imagine being an Earth scientist wanting to explore NASA MODIS data, it's pretty hard, especially if you want to do it on a long time scale. So exploration is a tough use case in this scenario. How do you explore this massive spatiotemporal array with all these wavelengths of data, et cetera? So my work in this process is in enabling scalable and interactive exploration, in this case of large array data, like the NASA MODIS. So coming from a database perspective, what a database researcher might say is, oh, why don't you just turn this into a SQL query and then throw it in a database, you're done. Mic drop, right? Well, if it were that easy, I probably wouldn't be presenting to you today. But database management systems are useful. So let's just give this a try. We can take the snow cover query, or the snow cover calculation I talked about, turn it into a SQL query. Here you see a stylized version. Apologies if you copy paste this and try to run it on a database management system. It won't 100% work, but for the purposes of a talk, hopefully it gets the idea across. You can take this, turn it into a calculation that you do in a database management system. And this will get you a lot of the way there. Database management systems are designed to be efficient. They're designed to process the data as efficiently as possible, but they don't really have a notion of interactivity. Of someone interacting with an interface, with a visualization, panning, zooming, dragging, clicking, those kinds of things. Database management systems don't care about that, so they're not really optimized for that. So you're not really going to get interactivity per se. It'll be efficient, but not necessarily interactive. And that's where my work comes in. So with my research, I take advantage of knowledge and methodology, not only from database management systems, but also from visualization systems, user interfaces, interaction design, and I combine them to enable innovative optimization techniques. So for example, in this case, you could develop an optimization layer that takes information from both sides, not just the database management system, but also the actual visualization interface itself. In this particular case, let's say a user is panning and zooming to explore the snow cover data that I have been talking about, where in this case, regions that are more likely to contain snow are represented as dark blue, and this user is exploring the Sierra Nevada mountains in California. If you can anticipate what pans and zooms a user is going to do, you can actually translate that into data processing operations that would be executed on the database management system. So then if you can predict a particular pan and zoom, you can essentially predict the computation that's supposed to happen in the future. And then if you do that speculatively in advance, you can actually reduce the perceived response time of the system. So in this way, you can take a behavior-driven or more user-focused approach to optimization and get similar performance benefits as more traditional optimization techniques. So now I'll just go into a little bit more detail about, what does it mean to improve performance for exploration from a more human-centered perspective? How does performance actually matter? And what kind of system did I build to address these challenges? So you might be wondering, okay, sure that you might make things faster, but what does that mean and how does that actually affect people? Well, that's a great question. So in this work that I'm going to talk about, we conducted a user study to evaluate exactly this. So given a system like this, if there's latency in this system, how does that affect people? So as you'll notice in this video that I've been showing you, there are these dashed lines. Those represent tiles. So we take this large image, cut it up into pieces. This will be reminiscent, hopefully, of, say, Google Maps or other kinds of tile-oriented or map tile-oriented visualizations. What we did is we took that and we abstracted it. In this way, we could control for how much information people have about the visualization, because admittedly, people already have a ton of information about maps. So if we ask you questions about them, it's not really going to be based on what you see on the screen. It'll be based on what you already know in your head. So if we abstract it, you can't take advantage of that. So everyone has the same information. And so we can see more general exploration patterns based on what people are seeing on the screen versus what they already know in their head. So instead of these beautiful maps, people saw these beautiful birds instead, and we asked them to explore this image collage, looking for a particular point of interest, which in this case was a dinosaur. And then what we could do is we could modulate the latency that people observed as they were panning through this collage. So here, the letter U represents the user's current location in this collage. We created two targets. So for example, two dinosaur images. One we called the low latency target, and the other we called the high latency target. And the idea is if the user starts panning towards a particular target, we could make the images that they see along the way appear faster or slower based on which target they were moving towards. For example, if they're moving towards the low latency target, the tiles that they would see, the images they would see along that path would appear faster. In the direction of the high latency target, the images would appear slower. And the idea is, if latency has an effect, then it's possible that it might influence which of these two targets a user would run into first as they explore. And if it does have an effect, that could also imply that latency could introduce bias in the way people explore their data. So here the light gray means lower latency appears on that part of the collage, and then the darker area means higher latency appears on that side of the collage. So taking the data that we collected from this experiment, we calculated a logistic regression model. We're on the x-axis. The independent variable that we're using to predict is the worst case latency observed by that participant. And on the y-axis is the probability that they saw the low latency target first, that the low latency target was the one that they found first. So what that means is, for example, if the prediction probability is really high, that means it's really likely that they explored the area around the low latency target more than the low latency target, or they preferred that part of the collage over the high latency region. And what's interesting here is that as you increase the worst case latency observed by participants, you do see a gradual increase in the probability that participants will find the low latency target first, meaning that as latency worsens in the system, as it takes longer and longer for tiles to appear, then the more likely it is that people's exploration behaviors are going to become more biased towards the parts of the collage that are less affected by latency. What's interesting as well about this result is originally, based on what we saw in the literature, we were planning on seeing, we had hypothesized that we would see more of a binary effect to latency. So for a while, it won't matter until you reach some magical threshold, and then suddenly it will matter a lot. But we don't really see that here. We see this weird subtle thing where you almost can't tell that the latency is getting worse, but clearly something is getting worse. So we found these results generally pretty surprising. And some of our main takeaways from it are the worse the latency is, the worse people will perform in terms of potentially having a biased exploration. And so the more you can reduce the latency, the better. But we also find in the literature, there are other latency studies people have performed, and they actually do find some thresholds that seem pretty interesting. For example, with thresholds even as low as 500 milliseconds, people might still perform worse in their exploration. So if the latency is 500 milliseconds or longer, people might perform worse. So taking our results, comparing, and then adding it to what we see in the literature, we pick 500 milliseconds as a starting threshold for how we could optimize systems. So just to make this more concrete, we'll talk about the full process end to end of what it looks like for optimization. So where are the points at which latency can occur in this exploration process? Starting from the beginning, the user has a query they want to visualize. They issue it to the system. In order to produce a visualization efficiently, the system might need to do some preparation in advance. For example, if you want to show a tiled visualization, you have to compute tiles. If you're a traditional database management system, maybe you want to build indexes, etc. So there's this pre-computation that happens. Then finally, a visualization is produced, for example, the snow cover visualizations that I've been showing you. Then given a visualization, the user will want to pan and zoom or do the interactions that they want to perform. Then the system has to respond to those interactions by fetching the corresponding results from the database management system. And then they need to update their visualization on the screen so that the user can take advantage of those updates. So there are these two loops. One is an interaction loop. So the user performs interaction, the system provides a response. The other is user submits a query, the system provides an interactive visualization. There are 2 points at which the system can introduce latency into the process. And we call this materialization latency and interaction latency. In this talk, I'm only going to focus on interaction latency, where in the literature, they find that a threshold of 500 milliseconds is helpful in terms of avoiding impacting people's exploration performance. And then pairing that with our latency results, in general, minimizing latency as much as possible is good. 500 milliseconds is our benchmark. So I'll talk a little bit about the space of potential solutions for optimizing here around the time that the system I developed was created, which is Forecache. So you can divide this optimization space first by how you take large data sets and then make them smaller to fit on the screen, for example, by aggregation or by sampling. You can then further partition the optimization space based on at what point you apply your optimizations. For example, offline at this pre-computation stage, maybe building data structures, materialization. If you're familiar with data cubes, that's where data cubes will be built. Then there's this predictive stage where right before the user is going to perform an interaction, you can try to predict what they're going to do and then provide some preventative response. And then finally, after the user's performed an interaction and you need to provide a response to them as quickly as possible, you could do maybe a progressive or incremental or sampling style technique where you show them an initial result, it might be kind of rough, and then if the user waits, they'll get a better and better result over time. So specifically for aggregation, since we're working with arrays and panning and zooming and whatnot, the work that I developed, which is Forecache and an extension of it called Sculpin, focuses on all of these 3 optimization strategies, specifically for aggregation-based visualizations. So I'll talk a bit more about the system I developed called Forecache, which supports detail on demand or pan-zoom browsing of large arrays, where Forecache has one of these middleware layers sitting server-side that I mentioned earlier. So it has a modular optimization layer that I'll talk about. So the contributions of the Forecache project are an analysis model describing how people explore array data. And then we use this analysis model as the basis for developing our optimization strategies, where the specific one I'll talk about today is predictive data prefetching, but I did develop some other optimization strategies that support this idea of predicting and anticipating user interactions. And then we evaluated forecast with 2 user studies. I'll talk about one of those user studies today. So just as a brief aside, forecast doesn't just support visualization and interaction in one view along just 2 dimensions. You can actually explore as many dimensions as you want. It's just a matter of what interface you specify to forecast. So here we're exploring 2 dimensions, latitude and longitude. That's where the panning and zooming on maps comes in. But say you wanted to explore along latitude, longitude, and time, you just have to add that view to your, for example, your dashboard that you tell forecast about. And then it says this isn't limited to even 3 dimensions. You can have as many as you want. It's just a matter of how you design the dashboard that you tell forecast about. But I'm going to focus on just the latitude, longitude version. Okay, so now how do we go from this, NASA MODIS data, raw, massive matrices to this actual dashboard interface that I'm talking about? Well, the data model underneath is what I call a tile-based data model. And the idea is that you want to take the array data, turn it into zoom levels, and then turn it into tiles. So given the data set, which is represented here as this grid, we do what's called windowed aggregation. So we aggregate every n cells of the array. And to make a coarser grain zoom level, we use a larger n. To make a finer grain zoom level, we use a smaller n. And what this does is it produces a series of zoom levels represented by this yellow box. And then what we do is we take each zoom level and we cut it up into pieces, equal width pieces, which are the actual tiles. And this is a simplified version of what forecast actually does. For example, almost no one explores 100% of every single zoom level. You can actually be a lot smarter than that. And forecast is a lot smarter than that, but I just don't have time to talk about all that stuff right now. Just take my word for it. So let's talk about the kind of more general architecture. So with forecast, we have a visualization front end, which runs in your browser, and that's in charge of managing the different views that I talked about that happen in this dashboard. Then there's this optimization middleware layer that I mentioned, where the first half of it is this prediction framework. So it takes information from the front end about what the user's been doing recently and makes predictions about when interactions it believes are going to happen next. Those predictions and then other requests from the user get translated to a tile builder component, which is actually in charge of taking these fetches, these requests from the user, and turning them into actual database queries that can be executed on a database management system. The particular system we used in this work is SciDB, because SciDB was designed to optimize specifically for array data. But you could use whatever backend you wanted. And then throughout every layer of forecast, we have tile caching for more efficient management of tiles at all levels of the system. Okay, so now I want to talk more about the predictive data prefetching techniques that I developed for forecast. That's the particular optimization I'm going to focus on in this talk. And to motivate that, we first need to understand, okay, well, how do people tend to explore array data? And that's what this 3-phase analysis model describes. So I say that people move through 3 phases of analysis. You can also think of them as sort of goals or sub-goals. If Ben Schneiderman were here, he'd probably say, hey, this looks a lot like overview, zoom, and filter, details on demand, which is another paradigm for thinking about how people explore data in general, not just array data. But the labels don't matter. What matters is the behavior that each of these labels represents. So rather than trying to tell you that my jargon is more important than someone else's jargon, I will instead just say, well, look at the scenario. Here's how we apply the labels. Guess what? You can train machine learning models to learn this, and we'll go from there. So let's take an example with snow cover here, where in this case, regions that are more likely to contain snow are red, and regions that are less likely to contain snow are going from green to blue. We're at a coarse grain zoom level, and we're looking for something interesting to explore. This is what I refer to as the foraging phase, because you're looking around, you're foraging for something that you want to investigate. Say this mountain range here. Then what's next is to zoom into that area so we can see it in more detail. So then we switch to the navigation phase where we're, literally navigating to that particular region of interest. Then we switch to the sense-making phase where now that we're at a finer grain zoom level, we can explore this region in more detail. Maybe we have some questions of our own that we want to answer, things like that. And then as part of the exploration process, these little dashed dashed line boxes represent the tiles that are being fetched and forecast along the way. That is Battle Data Lab. So once you have finished exploring a particular region of interest, then you switch back to the navigation phase to zoom back out so that you can return to this foraging phase so that you can look for other regions of interest that you might want to explore, such as this patch of red pixels in the bottom right-hand corner. And this happens in a loop. So given these three phases, sense making, navigation, and foraging, I developed a prediction strategy. So given a user's recent interaction, predicting what tiles should actually be fetched in forecast next. So let's say we have this visualization here, and the user just performs a panning interaction. We take this information, pass it to the first level of my prediction framework here, or my prediction strategy, where the first level is the phase predictor. So, given the user just did this pan, the phase predictor says, well, I believe it's likely that the user is in the sense-making phase. So given this particular phase that the person's in, then we run what's called the model manager. So what the model manager does is it has multiple recommendation models that it's in charge of. And each recommendation model represents a specific kind of exploration behavior that that particular model is tailored to detect, basically, or to predict. And what the model manager says is, okay, well, given the current phase, certain models might be better than others at predicting the behavior associated with that phase. So for example, if model 2 is better at predicting behaviors for sense making than model 1, we might allocate more space to model 2 than model 1 in terms of what model 2 is allowed to recommend for us to prefetch next. So then we run the models, they each make their recommendations on what tiles to fetch next. We consolidate that into a list that we send to our tile building component in our optimization middleware, and then we actually fetch the tiles. So forecast is not limited to 2 models. You can have as many as you want as a plug and play design, but the idea here is that it's good to have a starting point. So I developed 2 models in particular that we use in forecast. So the first is what I call the action-based recommendation model. So the idea is that it tries to capture the case when users are consistently moving in predictable directions. And this can be captured with something very simple, such as a Markov chain, or just a very basic Markov model. So to demonstrate how the action-based recommendation model works, let's say we're exploring this same visualization that we've seen before, snow cover, and we're panning right and then down and then right some more, and then maybe eventually we go down some more. So intuitively, when we look at this, we say, oh, that person's panning diagonally along this mountain range. Well, I'm not going to sit here and tell you that that's literally what a Markov chain is going to do. But what I can tell you is that it captures simple patterns and sequences and can extrapolate. For example, maybe it'll capture the right and then down again. So another recommendation strategy for picking out what tiles to fetch next could be that instead of fixating on the specific interaction someone performs, such as pan right or whatever, you could instead focus on the data that was fetched by those interactions and say that the user probably wants to see more of the same thing that they've been exploring recently. So in that sense, we can actually look at what tiles were fetched recently by the user's interactions. We can calculate what I call a signature for each tile, basically an ID of that tile representing the important characteristics within the tile. And then you can compare these signatures across tiles to say, okay, these tiles look more relevant, so we should fetch those next. So to show you an example of how this might work, here we are exploring the same data as before, but this time, let's say the user pans down 3 times in a row. And then these boxes represent tiles, where the one in the middle is the user's current location, and the ones around it are the neighboring tiles. So if we use the action-based recommendation model, it would predict that the user would pan straight into the Pacific Ocean, which, since we're exploring snow cover, we know that's probably a bad prediction. Instead, the signature-based recommendation model would look at the neighboring tiles, see that these ones look similar to what the user's been looking at in the past, and then make a prediction based on that. For example, maybe the user will pan right or up back the way they came. In this case, the specific interactions might not even matter. Once we know about the tiles, that's the important part as far as prefetching goes. So we calculate a range of signatures that could be as simple as, calculating a normal distribution or a histogram over a particular attribute in a tile. They could be more sophisticated as well, such as computer vision techniques. So for example, I created an image of every tile, just a very crude image, and then calculated scale invariant feature transform on top of it. So a pretty well-known computer vision technique. I am not a computer vision expert. I definitely do not claim to be one. But they have some pretty useful techniques that I've applied. So in the case of SIFT, the way it works is that it extracts key points from images. And you can kind of think of these as basically landmarks within an image. And the idea is, with these landmarks, with these key points, is that even if the image is bigger or smaller, the same key points should still apply. And this is pretty nice for forecast because, I mean, let's be for real. If you're zooming in on a mountain range, it's probably still going to look like a mountain range at a high resolution. So hopefully SIFT would be useful. So what we do is we basically use it's very much like bag of words, but it's bag of key points basically. So we calculate key points for all of the tiles. We make clusters for the key points, and then we calculate the total representatives within each cluster for each tile. So then we have these sets of histograms for every tile, and we can use the histograms to compare similarity. So we ran a user study. Well, we ran 2 user studies, but I'll talk about the one here. The first one, where we had 18 earth science researchers exploring snow cover using forecast with the same visualizations and videos that I've been showing you throughout this presentation. And the first thing that we did was we analyzed our 3-phase analysis model, because if the analysis model doesn't make sense, then basically the entire prediction structure doesn't make sense. And we found that, thankfully, 16 out of the 18 participants their exploration behavior did match our analysis model. So the next stage of our analysis then was to evaluate the performance of forecast. So in this case, we took the data collected from our user study, where I want to stress here that with the user study, when we were having people explore snow cover with forecast, we did not allow for latency in the system, since with that other study, we saw that latency introduces bias. We didn't want to see people's biased exploration. We wanted to see unbiased exploration. So we made this idyllic scenario where people explored, beautifully pre-computed snow cover data, and they explored that. And then we did a retrospective analysis to see, okay, well, if we make this scenario more demanding, would forecast be better compared to a non-prefetching baseline, and would it be better than existing prefetching techniques? And then the 2 existing techniques we evaluated were momentum and hotspot, where momentum means we predict that the user will just literally move in the same direction that they just moved in. So if they just panned right, then they're just going to pan right again. With hotspot, it aggregates information from people who've explored the data in the past. And if the current user is exploring a region that a lot of other people explored, then hotspot will predict that that person will move in the same direction towards hotspots that we know other people have explored. And then in the absence of information, it will just predict momentum behavior. So the results are that overall forecast provided a 20% improvement in accuracy compared to these other techniques. These are prefetching techniques. A correct prediction resulted in 20 milliseconds of latency in the system, and an incorrect prediction resulted in 1 second of latency in the system to go and get everything from SciDB and bring it back and process it and whatnot. So here we see a plot where on the x-axis we have the number of tiles predicted before each user's interaction. So for example, if k is 4, then that particular prefetching strategy was allowed to prefetch 4 tiles before every user interaction. And then on the y-axis, we have the average response time in milliseconds. So on average, what was the gap between when a user request was received and when a response was provided back to the front end? This dashed line represents our interactivity threshold of 500 milliseconds. And we see this red line, which is forecast, is lower than the other lines. So yay. Basically, we find that forecast was 88% faster compared to existing prefetching techniques, and 400% faster than a non-prefetching baseline. So if you don't prefetch at all, in which case every single user request is a miss, and then you have to fetch it from SciDB all the time. So prefetching is a good idea, and it's an even better idea when you use forecast versus existing techniques, at least the existing techniques at that time. So just to summarize, so Forecache provides several contributions. So an analysis model explaining how people visually explore array data, 3 behavior-driven optimization techniques, but I focus here on predictive data prefetching, and then 2 user studies to evaluate Forecache. I talked about one of those studies with earth scientists. And then overall, we have found that Forecache enables scientists to interactively and iteratively analyze large multidimensional data, where the iterative part comes from these other optimizations that I was not able to talk about today. Okay, so from this work, you might be saying, okay, that's great. Forecache seems pretty useful for earth scientists, but what about me? If you're evaluating Forecache for me, what should I be using? Should I be using Forecache? Should I be using some other system? Help me out here. Well, what if we try to answer that question with the systems we have right now and just their evaluation data? So we have my experiment data, we have their experiment data. What can we do with this? Well, there are a number of other systems that have been developed for interactive data exploration, particularly with visualizations, and a lot of them actually have been shown to support exploration of map data. The problem, though, is they weren't using the same map data. They certainly weren't using NASA MODIS satellite imagery, and they weren't using the same tasks either. So yes, they have experiment data. Yes, I have experiment data, but that data is not really comparable. There are other systems as well that could be of interest. Chirix in particular is actually an extension of Forecache in a way. The problem, though, is they don't actually have any performance-oriented user studies that we can compare. So the answer to this question, unfortunately, with the literature as it stands, is we don't really know what the best system is empirically, because these systems were never actually designed to be comparable. So the work I'll talk about next aims to address this problem. So I argue, and many others in the community are starting to argue more now too, is that we need more standardized evaluation methods. So for example, if you want to evaluate 2 different systems, you should probably evaluate them with the same or at least very similar analysis tasks. You should use consistent metrics. For example, if I'm evaluating latency, then you should also evaluate latency. The same input data sets should be used. If I'm using NASA MODIS data, you should probably also use NASA MODIS data, et cetera. And if you look at these parameters, they basically are the same as the parameters used in the database community for designing evaluation benchmarks. So what I'm really arguing for is a benchmark. So it might not be clear what benchmarking looks like from an exploration perspective. So let me talk about that more here. So here we have an interactive analysis system, for example, Forecache on the right, and on the left, we have the major components of what you would typically see in a database benchmark. So you'd have a workload generator, data generator, and evaluation metrics. What a data generator does is it creates an input data set that you would load into your system that you would then use for evaluation. And what's great about a data generator is you can usually adjust the data set size. So you can see how performance scales as the data set increases in size. You can also do things, for example, make it skewed, adjust correlations between attributes in the data, et cetera. Then you would use the workload generator to drive inputs to your interactive analysis system to trigger computation within the system that can be measured. For example, with Forecache would be triggering panning and zooming, and then later queries on SciDB. And then you'd use evaluation metrics to measure the results of executing that computation. So for example, average response time is what we focused on with Forecache. So we want a benchmark that would enable this, ideally. So I would be lying to you if I tried to tell you that benchmarks don't already exist. Technically, there are benchmarks out there in the visualization and the database communities. They just don't work very well for exploration purposes. So the major weaknesses of benchmarks on the visualization side is that they basically tend to be just data repositories. Hey, here's a use case we studied, here's some data. Hopefully it's useful to you somehow. Write your own code to figure it out. That's basically how benchmarks in visualization work, which, I mean, you can get it to work, it's just not particularly replicable. And then on the database side, it's the opposite. They have lots of code, they're industry standards, you know exactly what they're evaluating. It's just what they're evaluating basically is not really on the same planet as exploration. So I'll take the the standard analytics benchmarking databases as an example, TBCH. So TBCH is designed to simulate data warehouses. It's not really designed to simulate ad hoc or interactive exploration of an individual person. So overall, the landscape looks pretty bleak if you want to benchmark for exploration. But there are some really nice properties of these benchmarks that we want to preserve. For example, dataset customization, having an explicit workload that you test against, but also realistic data exploration scenarios, which the visualization community does very well. They just don't systematize them into runnable benchmark code. So to address these challenges, I led a large interdisciplinary team in developing one of the first database system benchmarks for supporting real-time interactive querying of large data. And the major contributions of this work are that we actually collected data from a user study of people exploring data using real-time dynamic query interfaces, particularly cross-filter. We took the data from the study, turned it into a runnable benchmark. And when we ran it, we actually found that none of the database management systems we tested provided satisfactory performance to support a cross-filter use case, even from what in the database community would be considered modest data set sizes. So we focus on cross-filter because it's a pretty demanding use case and it's gotten some recent buzz in the database community. And in particular, interactive for cross-filter is different from interactive even for forecache, because for forecache, our threshold is 500 milliseconds. But if you have to give real-time feedback as someone's dragging a slider, you need even stricter performance guarantees. And that's what cross-filter does. And it's a very demanding use case that is actually a really nice motivator for the database community to design more optimizations in the future. So that's why we focused on cross-filter in this particular benchmark. Cross-filter is a really nice stress test. So what do I mean when I say cross-filter? So in this particular case, I mean basically a dashboard where you have these connected visualizations where as you're performing interaction, so not after the interaction is performed, but while it's being performed, you get real-time feedback. So I'll just play a video here as an example. So here you have connected histograms of flights data. Here the user is performing a filtering interaction on departure delay in minutes. And as you'll see, as they create a filter or drag a filter around or adjust a filter, all of the other histograms that are connected update in real time. So the first thing we did was conduct a user study with some certain research questions in mind. So what patterns might we see as people interact with cross-filter interfaces? And then how do we take what we observe and translate that into implications for database management system performance? So to do that, we conducted this study with 22 participants using cross-filter interfaces like I just showed you. They explored 2 out of 3 data sets, movies, flights, and weather. We had them complete a series of subtasks that commonly occur during exploration, where these subtasks were based on some of my prior work that I don't have time to talk about today. And I won't talk about all of the results, but I'll call out a couple of things from this study that we observed. So for one thing in the database community that folks might argue is that, well, you know, real time, who needs real time querying? Is that really that important of a use case? What we find actually is that given the option to use real time interactions, people take advantage of it. So here's a bar chart showing for the different interaction types we observed during the study, how often we saw people using them. And we see that dragging brushes, so that particular interaction you saw in the video where as people would drag, the results would update in real time, that interaction is used twice as much as any other interaction in the study. So the only conclusion we can draw there is that, hey, this gets used a lot. Maybe we should support it, database community. We also find that when you partition the tasks we ask people to do into more complex and less complex tasks, we find that higher complexity tasks tend to result in more interactions and then less time between interactions or less think time. Meaning the exploration tends to be faster and there tends to be more of it when exploration subtasks tend to be more complicated. So here's a series of box plots divided by data set explored and complexity of task, and we see that the more complex tasks tend to have more interactions performed. We also find that cross-filter leads to high query generation rates. And this piques the interest of the database community in particular, because if, for example, one visualization in cross-filter can generate 174 queries per second, that is a lot of queries for a database management system to have to service. But that's just one visualization, right? If you remember the cross-filter visualization that I showed you before, that interface, if you update one filter, 5 other visualizations have to be updated. Each of those represent a different aggregation query happening on the database. So you actually have to take that number 174 and multiply it by 5 in this particular scenario. And that gives you a more accurate representation of what a database system has to contend with in a cross-filter situation. So thousands of queries a second is a lot, or potentially up to thousands of queries a second is a lot. So this seems like it'll be a pretty exciting use case for the database community. So to talk more about how we translated our interaction data into actual queries to be evaluated on a database management system. So we took those logs, translated them into SQL queries using IDE Bench. And then we tested 3 different data set sizes, so 1 million, 10 million, and 100 million rows. And we tested 5 different database management systems. Some known for being great analytic systems like MonadDB and InductDB, and some just because they're very, very popular, like SQLite and Postgres. So I won't talk about all the performance results, but I'll talk about response rate in particular. So with response rate, what we measured was for all of the queries issued by the cross-filter interfaces that we studied, what percentage of them were successfully completed, so they were not dropped by the database because the database took too long to get to them, and were they successfully completed on time? So did the query complete within 100 milliseconds or less? So if you look at the 1 million rows case, this is the smallest data set case that we studied. Several of the systems actually don't provide very good response rates. For example, Postgres, well, admittedly, Postgres is not an analytics, known as an analytics system, but this basically shows that Postgres is definitely not an analytics system, not an interactive analytics-based system anyway, because it only services in the best case 12% of the queries from our interface. So maybe if you're gonna build a cross-filter dashboard and connect it to a database management system, don't pick Postgres. But what's interesting is, even for systems that perform really well in a small data set scenario like DuckDB, it has almost perfect accuracy or almost a perfect response rate. You just do a modest increase of data set size. So from 1 million to 100 million rows, which is really not that big in the grand scheme of things from a database perspective. And the performance degrades significantly. So you go from 94% response rate to at best a 29% response rate from the best performing system out of all the ones that we tested. Meaning 71% of those queries got dropped or were not completed on time. So there's a lot of work to be done in the database community. And for reference, we compared some of these same systems with standard database benchmarks, and they perform 4 times faster. One benchmark, the star schema benchmark, it's based on TPCH, standard benchmark in the database community. MonadDB performs 4 times better, basically, on that benchmark than this one. So some major takeaways of this work are that real-time querying is an important use case, and the database community should study it. When people are given the option, they will use real-time results. Current database management systems and benchmarks don't seem to consider the cadence of real-time querying. So none of these queries generated by cross-filter are, queries that literally no one's ever seen before. These are just standard aggregation queries. What's unique is the cadence and the flow at which those queries occur, which are not captured in existing benchmarks. And then finally, we wouldn't know this if we didn't do this collaborative process between the visualization and database communities to actually collect this information and turn it into a benchmark. So rather than making assumptions about what should or shouldn't be done in terms of optimizing database management systems, we should really go out and collect the hard data to prove to ourselves that our systems really do work and that we really are focusing on the use cases that really matter. So in summary, I presented a new database performance benchmark. We conducted a user study to collect data on a particular use case for dynamic query interfaces, and we found that when translating that into a benchmark and running it with a number of systems, database management systems, that none of the systems we tested provide satisfactory performance, even with a modest data set size, at least modest in the context of database research. So now I'll just talk, I know we're almost at an hour here, but I do want to talk a little bit about some of my ongoing work happening in my lab. So first I want to revisit these research axes because that's how I organize my ongoing work. So optimizing, characterizing, and benchmarking exploration. So my vision for this work in designing exploration systems for exploring large data is to deepen the integration across communities of theory work, optimization work, and benchmarking work. So with optimizing exploration, I want to develop more intelligent and interoperable systems. So that means more intelligent models and also systems that can integrate more effectively with existing analytics ecosystems. Characterizing exploration, that would be developing more theoretical frameworks to help us reason from not only from a high level, say about user reasoning and interaction, but also down to low levels, for example, cost models, systems optimization levels. If we could connect those models together, that could be really powerful. And then finally, with benchmarking exploration, it's a lot of work to manually create a benchmark. It would be nice if not everyone had to run a brand new user study to create a new benchmark. And if someone already runs a user study, it might be really nice for them to just turn it into a benchmark automatically. So if we could find ways to dynamically generate benchmarks for exploration directly from experiment data, that could streamline the process of doing the systematic evaluation of exploration systems. And ultimately, what I would love, but I probably couldn't do by myself, it would be awesome if we had a community platform for sharing and comparing exploration systems and experimental results. So many user studies get run in visualization and even in databases, and that data doesn't really go anywhere. And it would be really nice if it went somewhere productive. We have to protect users, but it would be really nice if that data went somewhere productive so the community could take advantage of it. So I just want to make a little plug here for a system that is ongoing in my lab called Mirny. So the idea is that people want to design visualizations using languages like D3.js, but if you've used D3.js before, you know it's super hard to use, especially for new people who are new to it. So Mirny is designed to make predictions about what the user's trying to do with D3 and then automatically augment their D3 code to help them get to a completed interactive visualization faster. So here's a video showing what Mirny looks like. So given a data set, in this case, the iris data set, the idea is we could give the user templates of different visualizations they might want to create from their data, and then Mirny will automatically pre-populate that template with relevant parameters from the dataset schema. So in this case, the user is just adjusting the color scheme that Mirny picked out for the scatter plot of the iris dataset. And then Mirny can also recommend interactions to add to the code. And it ranks these interactions based on how often people have implemented that particular interaction type for the visualization type that you select or a visualization type that Mirny thinks you're creating. And then when you pick one, so in this case, the user picks a brush filter, Mirny will automatically augment the code to implement that brush filter for you. And the idea is to just have a broader sense of what it means to explore. People don't only explore using maps. People don't only explore using direct manipulation interfaces. They also explore in other modes. And this is one way in which we're trying to expand this focus and exploration in my lab from just direct manipulation interfaces to other kinds of interfaces. For example, interactive programming environments. We're also looking into Jupyter notebooks and other kinds of exploration environments as well. But I'm ready for questions. Thank you so much for listening to my presentation.